Okay. Welcome back to the session 4 of the differential equation. Here we are continuing the problem sessions of the first order linear ordinary differential equation. Generally we know that the first order linear ordinary differential equation has y dash plus p of x y is equal to g of x. Here p of x and g of x are the functions of x alone. This is the linear differential equation. If it involves y of x naught is equal to y naught, this is what is called the initial condition. A differential equation with the initial conditions is called initial value problem. In case of initial value problem, the point x naught is called initial point. Initial point. The function value y naught is the value of the function at that initial point. While applying this in general solution, we can find out a particular value for the arbitrary constant c. Say, consider the example, we can move to the example 3, that is the initial value problem. Y dash solve y dash plus y tan x is equal to sin 2x is equal to sin 2x, where y of 0 equal to 1. This is the initial condition. This is the initial condition in this question. So, while solving this differential equation, we can have this is the coefficient function of y, that is the p of x, and this is the g of x. Therefore, we have p of x is equal to tan x and g of x is equal to sin 2x, and we have to find out the integrating factor to solve this differential equation. To find the integrating factor, we have the formula. Integrating factor is equal to e raised to integral of p of x dx is equal to e raised to integral of p of x, the value of p of x is tan x dx. Integral of tan x, we have the formula for integral of tan x. Integral of tan x dx is equal to log sec x plus c, log mod sec x plus c. Therefore, this is equal to e raised to log sec x log sec x. E and log will gone, the remaining is sec x. Therefore, integrating factor we found as sec x. After finding the integrating factor, we know the solution. The solution, we have the formula for the solution. The solution is y into integrating factor is equal to integral of integrating factor into g of x dx plus c. See, y into integrating factor is sec x is equal to integral of integrating factor is sec x into g of x. G of x is sin 2x dx plus c. See, the right side integral of, I can rewrite sec x as 1 by cos x by the formula of trigonometry into sin 2x, again by the formula of trigonometry we know that sin 2x is 2 sin x cos x dx plus c. See, here we have denominator have 1 cos x and numerator have cos x. So, we cancel that and we will have this is y into sec x, y into sec x is equal to integral of 2 sin x dx plus c. This is y into sec x is equal to 2 into integral of sin x. Integral of sin x is minus cos x. I am taking this minus is here, minus cos x plus c. This in the left side C, the left side we can rewrite as 1 by cos x into y. Instead of sec x we can write 1 by cos x. 1 by cos x into y is equal to minus 2 cos x plus c. Therefore, we can take this cos x to be here, and here we can multiply y is equal to minus 2 cos x into cos x, again cos square x, and cos x into c is equal to c cos x. This is the general solution, that is y is equal to c cos x minus 2 cos square x is there. This is the general solution. This is the general solution for given ODE. This ordinary differential equation is linear, and this is the general solution because here it contains the arbitrary constant c. Now, we have given our problem is that the initial value problem, there is one initial condition is there. Because of that initial condition, we have to apply that initial condition. Definitely, because of it is a initial value problem, we will have a particular solution is there. So, apply initial condition. Apply initial condition. While applying the initial condition, we have y of 0 is equal to c cos 0 minus 2 cos square 0. Therefore, y of 0 we have given it is there, y of 0 equal to 1, c into cos 0 is 1, therefore, c is there, cos square 0 is 1, therefore, this is equal to minus 2. We have to find the value of c. I am taking minus 2 be here, c is equal to 1 plus 2 is equal to 3. Therefore, the value of c is 3. Apply the value of c is to be here in this general solution. So, what will happen is that y is equal to c cos x. Instead of c, we can replace the value as 3, c cos x we can replace as a 3 cos x, minus 2 cos square x, minus 2 cos square x, and this is what is called the particular solution of the given initial value problem, particular solution of given initial value problem. This is the particular solution of given initial value problem. So, this is the general solution. Firstly, we will arrive the general solution. That general solution should contains the arbitrary constant. The arbitrary constants are the constants that can receive the value as like a variable, they will receive the values as their own wish. But while applying the initial condition, it will be restricted to a single solution. That solution is called a particular solution. See, we can move to the next one more question of the initial value problem. Come to the fourth question. Example 4. Solve the initial value problem. Y x y dash plus 2y is equal to 4x square with the initial condition y of 1 is equal to 2. Y of 1 is equal to 2. Here y of 1 is equal to 2 is the initial condition, and 1 is the initial point. This is the 2 is the function value on that initial point. See, in this initial value problem, while seeing this is not linear, firstly we have to linearize this one. I am putting this equation as a star. To make the y dash is alone here, we have to divide this our differential equation with x. So, divide star with x. What will happen is that this is equal to x y dash by x is the y dash alone, this plus 2 divided by x into y is equal to 4x square by x is equal to 4x. Now, it is very easy to as is that this is the p of x and this is the g of x. Now, p of x is there, g of x is there, y dash plus p of x into y is equal to g of x. Now, this is the first order ordinary linear differential equation. See, we have to solve this one, as we did in earlier problem, we have to find out the integrating factor. To find integrating factor, we have a formula to find integrating factor. Integrating factor is equal to e raised to integral of p of x dx is equal to e raised to integral of p of x is equal to 2 by x dx is equal to, this is equal to e raised to 2 into integral of 1 by x dx is equal to e raised to 2 into integral of 1 by x is log x is equal to e raised to log of, I am taking this 2 to be power of x, log of x square. So, we have now arrived as e integrating factor is equal to e raised to log of x square. By the formula, e and log will gone, the x square only will remains there. That is why this is equal to x square. The integrating factor is equal to x square. For this problem, we found the integrating factor is there. The integrating factor is equal to x square, and this is will apply here. The solution of star is the actually the solution of the A, equation A, and the solution of star and A are the equivalent linear differential equations. This is, while seeing this is not a linear differential equation, by using some simple operations we convert that as a standard form of the linear differential equation. That is why the given differential equation itself a linear differential equation, and which have the integrating factor is equal to x square. So, we can find out the solution. Therefore, the solution is, the general solution is, we can find by the formula y into integrating factor is equal to integral of integrating factor into g of x dx plus c. See, what about g of x? Here this is the a is the correct function, this is equal to y is into integrating factor is equal to x square. Again this is equal to integral of integrating factor is equal to x square, and g of x. What about g of x? G of x we are taking from a. Here this is the p of x and this is the g of x. So, g of x is equal to 4x dx plus c. Say y x square is equal to 4 into integral of x cube dx plus c. By the formula of integration, we have integral of x cube, like integral of x raised to n. Integral of x raised to n is equal to integral of x raised to n dx is equal to x raised to n plus 1 divided by n plus 1 plus e. So, integral of x cube is equal to, therefore, the given equation will come as y x square is equal to 4 into integral of x cube is equal to x cube plus 1, that is x raised to 4 divided by 4 plus c, and we can cancel this 4 and 4. Therefore, this is equal to y x square is equal to x raised to 4 plus c is the general solution. We know that actually we have to make y alone, we are taking x square to be here as well as to be here. Therefore, y is equal to x raised to 4 divided by x raised to 4 x square, this is equal to x square plus c divided by x square. This is the general solution. This is the general solution of the given differential equation. Now, our differential equation is the initial value problem. Because of this is a initial value problem, we have to apply the initial condition to arrive at the particular solution. This is the given solution. What we found is that the general solution. Here we have the arbitrary constant C is here. We have to replace this C by applying this initial condition. What is our initial condition? Our initial condition is y of 1 is equal to 2. That is, whenever the point the x receives the value 1, the y receives, whenever x receives the value 1, the y receives the value 2. So, we can replace here like that, the general solution will come like this. Therefore, y of 1 is equal to x square, instead of x square it is 1 square will come, and c divided by 1 square is there. Y of 1 is equal to 2, therefore 2 is equal to 1 plus c. I am taking this 1 to be here, therefore c is equal to 2 minus 1, c is equal to 1. Now we found the value of c for a particular value for this arbitrary constant. That is why we say that the particular solution is, therefore the particular solution of given differential equation is, the particular solution of the given differential equation is y is equal to x square, instead of c we replaced by 1 by x square. This is the particular solution for the given differential equation. So, here in this we discussed two types of questions. One is just only a linear differential equation, second one is the initial value problem for a differential equation. There should be, in case of the first order, any of the first order differential equation, if there exists a one initial condition is there, there should exist a particular solution by using that initial condition. That is what is called, again I am telling it is that particular solution for this differential equation. See, I am discussing one more question for you, is that solve example 5, example 5. Example 5, example 5, y dash plus 2y is equal to 6 e raised to x. Simply this is a linear differential equation. We can compare with our general form, y dash plus p of x into y is equal to g of x. Here 2 is the p of x and 6 e raised to x is the g of x. Now the given itself a linear differential equation, and as well as which is not an initial, there is no initial condition, that is why this is not an initial value problem. So, that there is no particular solution is there, there exists only the general solution. So, we can write this as, we can find the integrating factor to solve this differential equation. Integrating factor is equal to e raised to integral of p of x dx is equal to e raised to integral of p of x is 2 dx, that is equal to integral of e raised to 2x. So, this is the therefore integrating factor. Now, we found the integrating factor as e raised to 2x. E raised to 2x is the integrating factor. Now, we can move to the solution. What about the general solution? We have the formula for the general solution, y into integrating factor is equal to integral of integrating factor into g of x dx plus c, g of x integrating factor into g of x dx plus c. See, what about the integrating factor? Y into integrating factor is e raised to 2x is equal to integral of integrating factor is e raised to 2x, g of x is the 6 e raised to x plus c, sorry dx plus c, 6 e raised to x dx plus c. Now, this is equal to y e raised to 2x equal to integral of, we can take 6 out and e raised to 2x plus x e raised to 3x dx plus c. Now, this is equal to 6 into integral of e raised to 3x, e raised to 3x divided by 3 plus c, e raised to 3 x divided by 3 plus c. Therefore, y into e raised to 2 x, y into e raised to 2 x is equal to, we can cancel 3 and 6, 2 is there, 2 e raised to 3 x plus c, 2 e raised to 3 x plus c. See, the last final case is y e raised to 2 x equal to 2 e raised to 3 x plus c. I am taking this 2 x to be here and here. Therefore, y is equal to 2 e raised to 3 x divided by e raised to 2 x plus c divided by e raised to 2 x equal to 2 into e raised to 3 x minus 2 x. I am taking this 2 x to be in upper part. Therefore, plus c e raised to minus 2 x. This is y is equal to. Therefore, y is equal to, what will happen? Y is equal to 2 e raised to 3 x minus 2 x, that is x is plus c e raised to minus 2 x, c e raised to minus 2 x. Now, there is no initial condition, that is why this is the final answer. This is the general solution for the given differential equation. Now, you can find out many questions related to linear differential equation by using, we can solve that linear differential equations by using the integrating factors. I left 2 more questions to do as an exercise for you. Example 6 y double dash, sorry, y dash plus y is equal to sin x, and example 7 y dash plus y is equal to cos x. You may try to solve these 2 questions. Simply you can find out in both cases p of x is equal to 1. In first case g of x is the sin x, in second case g of x is the cos x. So, simply you can solve as we solve these all questions. So, continue to solve these like questions. I like to move to the next part of the to finding solution of the first order linear differential equation. We mentioned it is there. There are 2 methods to find out the solution of the first order linear ordinary differential equation. The first one is we completed, that is by integrating factor. The second one we discussed, it is there, that is the method of variation of parameter, method of variation of parameter. It is a very simple part of the linear differential equation. Simply we can find out the differential equation. Generally we have the linear differential equation as we already discussed, it is there, y dash plus p of x into y is equal to g of x. This is the first order linear ordinary differential equation. If we are using the initial condition is there, again you will get the particular solution for this differential equation. And as well as, because this g of x not equal to 0, if this g of x not equal to 0, then this linear differential equation we are treating as a, that is a non-homogeneous, that is non-homogeneous. And if g of x is equal to 0, then we treat this as a homogeneous linear differential equations, homogeneous linear differential equations. See, if here for every differential equation, every non-homogeneous linear differential equation has a homogeneous part is there. We can consider its homogeneous part as homogeneous, its homogeneous part, that is y dash plus p of x into y is equal to 0. This is also a first order linear ODE. This is also a first order linear ODE. This is a first order linear homogeneous ordinary differential equation. As like every differential equation, this linear differential equation also have a solution. We treat this solution of this differential equation to homogeneous part, solution of 2 as y is equal to y of x is equal to a into e raised to minus integral of p of x dx, where p of x is, as we used in our finding the integrating factor, the coefficient function of x in coefficient function of y. So, this a, in this homogeneous part, this is the solution of the homogeneous part, that is the differential equation 2. See, this is in this differential equation a is a constant. In this differential equation a is a constant. And similarly, we have our aim is to find out the solution for the non-homogeneous linear differential equation. To find the solution for that non-homogeneous differential equation, we are replacing this constant a as a function in x. So, definitely we can say that if this is a solution of the homogeneous part, then y of x is equal to a of x. A of x is a function of x into e raised to minus of integral p of x dx is a general solution of 1, which is 1 is our non-homogeneous ordinary linear differential equation. So, our aim is to, by using this method, firstly we found the solution, then we will apply the solution in the non-homogeneous differential equation. By applying that is to be here, we can find out the value of a as a of x. After assuming this one, we will treat this a as a of x. A of x means here this is a constant, but here this is a function in x. By finding this function, you can identify, you can find out the general solution for this non-homogeneous linear differential equation. We can move to some of the questions by using this method. See, in this part, example 1 for this part, example 1, solve dy by dx minus y is equal to 3 e raised to x. Simply while seeing, we can identify this. We all discussed many examples here. This is the y dash is there, minus p of x into y is here, g of x is here. So, this equation 1 is a linear differential equation. Because of the this part is not equal to 0, 3 e raised to x is not equal to 0 always, that is why that is a non-homogeneous linear differential equation. So, by solve we have to solve this differential equation by using the method of variation parameter. How can we solve? That is by using the method of variation of parameter. We have the homogeneous part, homogeneous part of 1, sorry, equation 1. That is the non-homogeneous part of 1 is dy by dx minus y is equal to 0, and we suppose that this is equal to solution. I am treating this as equation number 2, and therefore, let the solution of 2 is let solution of equation 2 is y of x is equal to a e raised to minus integral p of x dx. Simply we can identify which is p of x. P of x is the coefficient of y, that is now here it is the minus 1. So, y of x, the solution of the homogeneous part a e raised to minus integral p of x is minus 1 dx. this minus and minus make it as a plus, this minus and minus make it as a plus. Therefore, a raised to integral dx equal to a e raised to x. So, for the homogeneous part we have a solution y of x is equal to a e raised to x is there. This is the solution of 2, solution of 2, solution of 2, where 2 is the homogeneous part. Now, we have to find the solution for the non-homogeneous part. So, we have to just convert this a as a of x. Make therefore, set let y of x is equal to a of x into e raised to x is solution of 1. Therefore, we can apply y of x is equal to a of x into e raised to x in 1. Put y of x is equal to a of x into e raised to x in 1. What will happen? D by dx of, instead of y of x, we can replace as a of x into e raised to x minus y as a of x into e raised to x, a of x into e raised to x, a of x into e raised to x equal to 3 e raised to x, 3 e raised to x. We can differentiate d by dx of a of x into e raised to x. We can treat a of x as a first function and e raised to x as a second function. So, derivative of a of x, that is the first function a of x into derivative of e raised to x, that is e raised to x, plus a of x, derivative of a of x dx divided by dx divided by dx into e raised to x minus a of x into e raised to x is equal to 3 e raised to x. Here I have 1 plus a of x into e raised to x is there, as well as here has 1 minus a of x into e raised to x is there. That is why we cancel that both, and now we have, it remains for us is that d by dx of a of x into e raised to x is equal to 3 e raised to x is there, 3 e raised to x is there. Now, we can cancel this e raised to x as well as this e raised to x. It remains for us only is that d a x divided by dx is equal to 3. Now, I am taking this dx to be here, derivative of a x, d of a x is equal to 3 into dx, 3 dx, integrating both sides, what will happen? Integral of derivative of a of x is equal to integral of 3 dx, is equal to integral of derivative of a of x is nothing, that is equal to a of x. Integral of 3 dx is there, 3 x plus c. Now, we found the value of a of x. Our assumption is that we assume that y of x is equal to a of x into e raised to x is a solution of the given differential equation 1. Now, we found a of x is there, that is why we can find the general solution. Therefore, general solution of one given linear ordinary differential equation is a y of x is equal to a of x into e raised to x, that we assumed. This is equal to, that is y of x is equal to, we can rewrite as 3x, a of x is 3x plus c into e raised to x is the general solution. It is the general solution. So, we have the general solution is here y of x equal to 3x plus c e raised to x. Here c is the arbitrary constant, and here we mention only the differential equation, since because of there is no initial condition, we have only the general solution is here, no particular solution will exist for us here. Now, I am left some 2 more examples for you that you can do as an exercise. Example 2, t y dash plus 2 y is equal to cos t, and example 3, 2 y dash plus y is equal to 3 x square. We may try to solve these two questions as we discussed here by substituting for the homogeneous part, as the solution is y is equal to a e raised to integral minus p x dx, and as well as you after that we replace for the non homogeneous equation y is equal to a of x into e raised to minus integral p of x dx as the solution. Then find a of x and substitute here, that is the solution of the first order ordinary linear differential equation, and this is the method to find the method of variation of parameter to solve the differential equation. This method is also we are using to solve the first order linear differential equation, and the first order linear differential equation is the one of the step for the differential equation, and we have many methods for the differential equation. Keep continue the watching. I will come to on the next session with another sessions of the differential equation. Thank you very much.